Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering.
So this is a stress versus strain plot, and what you are seeing here is a kind of a non-linear stress strain curve, also having different features. Let us try to understand this up to elastic region or up to the yield point sigma naught. In a microcracking material, how do we define sigma naught? That is the question. The slope is E naught, and there is something called sigma S, and then we are again uh, defining something called ES. This is a a reduced modulus, and this is the epsilon t. We will see all this. The stress strain curve for microcracking material subjected to a zero tension, zero load cycle. So this is there's no compression here. It is only tension. Cycle is it's only tension cycle. It is called zero tension, zero cycle. There's no compressive stress. Sigma S is a microcracking is assumed to increase and continuously until this level. So this is the moment it crosses this, that is a proof stress kind of thing, the material is expected to undergo deformation with the microcracking is keep on increasing in this material till this point. The microcracking is keep on increasing. Here we have to talk in terms of like what we have assumed in dislocation mediated plasticity in metals. The strain hardening takes place, and then the number of dislocations keep on increasing till it saturates, right? So similarly, the micro cracks keep on increasing till it saturates. There is no scope of further micro cracking. All the regions are consumed like a dislocation. Here, there is no scope of generating new dislocation. Here, it is no scope of creating a micro cracks. So it reaches the maximum. So that is called sigma S, saturate sigma. Above this level, sites for microcrack nucleation will become exhausted, and the local thermal residual stresses dictate the microcracking. So above this, it is only local thermal residual stresses will be dictating whether the microcracking will take place. Epsilon T is a permanent strain after unloading. So this is a reduced modulus, and then up to this is the permanent strain, unrecoverable, irreversible strain. So how do we understand this mechanism? There is a one nice model. When the microcracking material is subject to compression load, what happens? So this is very constitutive behavior of microcracking brings all in a cyclic compression. That is zero tension, zero. This is compression, cyclic compression. Zero compression, again zero. The total density of open microcracks which exist at the maximum compressive stress of fatigue cycle be beta max. So here we are defining a parameter based upon the during cyclic loading, whether the microcrack is opened or get closed. So that is the physics behind it. And the maximum compressive stress of the fatigue cycle is beta max. Okay. The total density of open microcracks. So all the microcracks are the total density. How many cracks are completely open? That is defined by this beta max. Fraction of microcracks of density beta u close fully upon complete unloading from the compressive stress. There is another parameter which measures the number of microcracks they get fully closed upon the unloading. So that means compression, it comes back to zero. So how many of the microcracks keep closing? The development of permanent strains after one compression cycle can then be quantified by an unloading parameter lambda, which is defined as lambda is equal to 1 minus beta u by beta max. Okay, so how do we understand this? The unloading path B corresponds to the idealized situation where all the microcracks of density beta max gradually close open upon unloading. That is, lambda is equal to 0. Okay, so what is B? The path B is shown here. It reaches 0. That means all the microcracks got closed. It just, while loading, it was just opening. When it comes back, it is closing. Okay, so here, similar to the earlier plot, here also you see that microcracks beyond which it goes. It's supposed to be sigma s. There is a typo here. Sigma naught and sigma s. Okay. So if all the microcracks get closed following this path B, then lambda is equal to 0. Path D is which represent the other extreme. All the microcracks are blocked by the debris within them, are locked by the friction. So all of them just kept open. Nothing come to close. So that is another extreme situation. So this is completely closed and this is completely open. If the frictional sliding taking place between the faces of the microcracks during compression partially reversed upon unloading, then beta u will be in between 0 and beta max, and the lambda will be in between 0 to 1, and unloading occurs along the path C. So this is a in between situation where the value of beta u, okay, it will be between this, okay, whether the fraction of microcracks only get closed, only fraction is closed, that is what defined here, beta u. And when it comes to that kind of thing, then this fraction, this equation will give the lambda is between less than 1, right, because it is less than 1. So this will be the unloading path C will be dictated by this. Okay, so this is one model which explains how the microcracking material will be, will be behaving when they subjected to cyclic loading. Okay, this one for tension, one for compression. This is what we have seen. So what happens at high temperature for this brittle material? Okay, this brittle material, this is a micrograph, electron micrograph shown for the silicon whisker broken under cyclic loads. Amorphous phase can be seen inside the whisker. So you can see all inside this, there are a lot of amorphous phase. That's what is reported. The growth of intergranular frost may be caused by the local diffusion process or by viscous flow of any amorphous films depositing along the train facets. And silicon carbide whisker reinforced alumina matrix composite. Silicon carbide forms, silicon dioxide viscous film forms, which is a glass phase when exposed at 1250 degrees centigrade. So what happens to this highly brittle material at high temperature? That is just given some example with some what are the new flaws and the new phase which comes and crystalline form and which becomes viscous flow or amorphous films formation. All these aspects are shown in this micrograph. The viscous flow of this molten phase leads to formation of cavities. So you can see that already there is a cavity here. This and here is a cavity. Here is a cavity. And the microcracks along the interface during the cyclic load. So all the interface will have several microcracks. You can see that. Here you can see a lot of microcracks. So now we'll turn our attention to semi-brittle solids. What happens? Ionic crystals have shown that pileup of dislocation that obstacles or at other dislocation can lead to the nucleation of cracks. In a semi-crystalline solids, similar to metals and alloys, you have pile-up of dislocations at the boundaries. Okay, and then you can see that grain boundary obstructs the slip in magnesium oxide and the transgranular crack in the magnesium oxides. Under some restricted conditions of temperature and strain rate, cyclic loading can produce slip bands and cellular structure in rock salt crystals. So you can see that slip bands are there. You can see the slip bands which are all forming. Okay, and cellular structure is also reported in the rock salt structure. Okay, so that's about the semi-brittle solids. Now I just want to give some idea about the transformation toughened ceramics. Very important topic and very popular in material science. Okay, transformation toughened ceramics constitute a special class of brittle solids in which plasticity can be introduced by means of phase changes under the influence of applied stress. You see, in a highly brittle material like ceramics, if you look at the fracture toughness values of this materials, you will be surprised. For example, if you take high strength steels, the fracture toughness values will be in the order of 40 to 80 MPa square root meter, right? But if you talk ceramics, fracture toughness will be less than 10 MPa square root meter. I mean, even 10 is higher, it's much lower than that. So improving the fracture toughness from, suppose if I have 5 to 6 MPa square root meter, or I have 2 to 3 MPa square root meter as a fracture toughness, if I can improve from this value to 6 or 7, or from 6 to 8 MPa square root meter, it is considered to be significantly successful process or successful attempt. That is the importance of toughening the ceramics. Okay, so that is considered the huge achievement. Okay, because ceramics are highly brittle, and we are talking about a fracture toughness. Right? So that is one. There are several ways people try to improve the fracture toughness. One of the popular method is improving the toughness through phase transformation. The phase change imparts a propensity for nonlinear deformation and for stable fracture in monotonic and cyclic loading. Okay, see we were talking about how to improve the toughness impact by plasticity induced crack closure and all. There are also toughness improving mechanisms. Here, if you consider the crack is there in the ceramic material, and then ahead of the crack the region is getting into or transformed into a new product, then what happens? That is the idea. Among all the transforming ceramics, zirconia, partially stabilized with magnesium oxide, is mostly studied. Okay, MgPs is a partially stabilized zirconia system. Tetragonal to monoclinic phase changes occurs as a martensitic transformation in ceramics which contain metastable zirconia. So metastable zirconia, which is originally having tetragonal crystal structure, changes to monoclinic crystal phase through martensitic transformation. Okay, that means just a simple shear. So this is one micrograph, shows a transgranular shear band formation due to martensitic transformation. So you see that there are some transgranular shear bands, and it looks like a lot of particles are embedded in a matrix. Yes, it is true. There are a lot of particles, but in order to make you little more appreciate this, what is shown here, I'm just showing this schematic. Suppose if your grain has having lot of lens shaped, zirconia particles, which is so this is supposed to be a schematic microstructure of a peak aged uh, MgPs partially stabilized zirconia containing 9 more percent of magnesium oxide. So what is shown here is a correlated transformation of particles leading to the formation of a shear band. So this is a shear band formation because each particle of zirconia is now transformed to a monoclinic phase. So that's what's shown here. What is interesting in the schematic is it is again based on the experimental evidence only. The transformed particles from the the tetragonal to monoclinic phase is having the same orientation. So all this this when you say that it is undergoing a martensitic transformation, locally the shear strain, okay, it will cause some shear strain, right? So when they are in the same orientation, the individual particle which experiences the shear strain will be totally, it will be a cumulative effect for the bulk. Okay, so in fact the orientation of this individual particle also contributes the shear band nucleation. Okay. What basically you have to understand is these particles are embedded in the elastic matrix. Okay, when obviously once the transformation takes place, then there is a volumetric strain as well as the shear strain, that you know, right? So this will trigger the shear strain. I mean especially the shear strain contributed by individual particle will trigger the shear band formation. So which will be contributing to the total bulk volumetric as well as shear strain to the bulk material. So that is how you should understand. For an unconstrained tetragonal to monoclinic transformation in magnesium PSZ, the maximum amounts of volumetric and shear strains are 0.04 and 0.16 respectively. Okay. Though individual particles will have the volumetric strain, this one, but if you look at the average shear strain of particles, always will be less than this. This is about unconstrained transformation. So the individual shear strain or average individual shear strain of this particle will be always less than the this value. This one has to remember. Okay, so what is so important by this? Permanent phase changes cause a stress strain hysteresis in transforming ceramics upon loading and unloading. So this is a stress strain behavior of the ceramic material which is after transformation. Please remember, ceramic materials we described as a very highly brittle solid. Now it is showing a non-linear stress strain response. Okay, after the improvement in the toughness, that is something which you have to appreciate. So beyond the plastic, beyond the elastic region, it also produces a permanent plastic strain upon unloading. But if you look at the elastic region, a non-linear elastic region, if you even unload, then it traces back to the same path, and then the elastic modulus of these two are almost similar. So what is it? It implies? We will just discuss after going through this point. Beyond a tensile stress of about 275 MPa, fully irreversible phase transformation takes place, resulting in a constitutive response becoming highly nonlinear. So that's what it is shown here. Elastic unloading is observed in a nonlinear region. Reloading occurs with an elastic modulus which is identical to that of initial elastic region. So this is what is shown here. See, even though it is a non-linear elastic behavior, after unloading, the elastic modulus is same if you reload again. So what is that we are now discussing here? So this phase transformation improves the toughness of the ceramics. We are evidencing that by stress strain behavior of this material, right? It is showing a non-linear stress strain behavior. That means the toughness is significantly improved. So what you have to understand here is in a metallic materials, we are talking about dislocation mediated plasticity. Here we are talking about transformation mediated plasticity. And one difference is in a dislocation mediated plasticity, it is volume is conserved, but contrarily here it is slightly different. That's what I just showed some of the numbers. The volumetric strain is about 0.04 and shear strain is what 0.16. Okay, so you can compare these two, transformation induced plasticity and dislocation induced mediated plasticity in the metal materials. So the final point to appreciate is the highly brittle material like zirconia, partially stabilized zirconia, can be toughened by the phase transformation in this material. So that is the idea. So now we will look at very briefly fatigue in the semi-crystalline and nanocrystalline solids. Craze in polymeric material, something related to metallic materials and non-metallic materials. Deformation, heavy deformation, severe deformation is always characterized by the formation of shear bands. In polymeric material, is something close to that is called craze. So the craze is shown in this micrograph. So this is a newly formed craze in a polystyrene, normal to the tensile axis and the fibrils parallel to the tensile axis. So these are all fibrils parallel to tensile axis, and this is perpendicular to this. The total entity is called craze, which is perpendicular to the tensile axis, and the details of these structures are shown here. So you can, all the fibrils are aligned along the tensile axis, and in between there is a voids. Okay. A craze contains fibrils of highly oriented molecules separated by porous regions. So what are the important points for the cyclic deformation of polymers? Cyclic softening is a general fatigue phenomenon in ductile polymers, irrespective of underlying molecular structure. Amorphous and semi-crystalline polymers as well as polymeric matrix composites exhibit cyclic softening because of molecular rearrangement. This is quite understandable. We have seen that amorphous materials and polymeric material deformation in while we were discussing tensile deformation. It is completely molecular rearrangement, right? That takes the complete control, right? And homopolymers develop a stable hysteresis loops. During cyclic softening, strains are accommodated by molecular rearrangements at microscopic level, whereas the monotonic loading promotes more macroscopic permanent deformation associated with the molecular rearrangements. So the cyclic behavior is quite interesting in this polymeric material. Just let us see that. What you are seeing here is the hysteresis loop. You see, it is completely a non-linear, I mean, an unusual hysteresis. I would say not. It's not non-linear. It is not symmetrical, asymmetric, completely asymmetric. So what is this reason? Before it reaches the saturation, it undergoes all this. Change in size and orientation of hysteresis loops with the progression of fatigue deformations in a polycarbonate is shown here, which is subjected to strain controlled fatigue at 298 Kelvin. Okay, so this is a typical characteristic of hysteresis behavior exhibited by polymeric material. And what is shown here is a monotonic versus cyclic. There's a huge difference. Okay, this is what the last point in the previous slide mentions. The cyclic behavior is quite different from the monotonic behavior because of the even the monotonic behavior, it promotes hardening because of molecular arrangements oriented along the tensile axis. It promotes a cyclic hardening, but a cyclic sorry, not cyclic hardening, monotonic work hardening. In a cyclic deformation, it is completely dominated by the cyclic softening because of the molecular rearrangement and collapse. So, in a typical fatigue cycling, there is an anomalous fatigue behavior by the polycarbonate at 77 Kelvin. What is anomalous about this? Since craces form only under local tensile stresses, cyclic softening is observed only in the tensile portion of the fatigue, and the hysteresis loop remains stable in the compression portion. Very interesting. In polymeric material, we talk about craze formation and how it responds to the applied load. So when it becomes a complete, reversal cycles like tension compression kind of fatigue, in tension the craze will form, in compression it will be a normal behavior. So this is a very interesting behavior. This type of anomalous is indication of a stable crack growth of microscopic cracks under fatigue load. So even in polymers, we are talking about a stable crack growth, right? If you recall, in a fracture mechanics, very interesting chapters we have come through. We use the R curve to talk about, stable crack growth, right? So in this kind of polymeric material also will come under that category. There are R curve material. Okay, any material which exhibits stable crack growth, they are also preferred in literature like R curve materials. So very interesting point to remember. And finally, I just want to briefly discuss about the fatigue crack growth in polymers. Very interesting point. A sequence of optical photographs taken after every 100 stress cycles of loading, which show discontinuous crack growth in a polycarbonate by formation of epsilon shaped deformation zone. You see, it is an epsilon shaped deformation zone. Why it forms? Yeah, we will now see why it forms. So this is a typical dA by dN versus delta K crack growth curve. And this photograph is very magnified version of the same crack growth. So what you see here is very interesting events. You just closely observe this. Ahead of the crack tip, the craze forms. You can see the craze. The craze is forming here. But this shear band is forming at the angle of 45 degrees. So ahead of the crack, the craze forms, and then it just moment the craze forms, then it branches into shear bands. So the shear band formation takes place as the crack advances. First craze forms, shear band forms, and then craze forms, shear band forms. So it is called shear craze mechanism. Shear craze mechanism. Okay. Shear band cracks ahead of the fatigue crack in a polycarbonate. The crack propagation from a free surface by a combined shear craze process, which leads to an epsilon shaped lateral profile. So because of the shear craze process occurs quickly, and you can just go back to and see now this one. What happens is once it forms like epsilon shape shear bands, the crack immediately jumps. It doesn't carry the deformation there. It just jumps from there. So that is what it is shown here. This apparently beneficial and anomalous behavior associated with the epsilon fracture process has been attributed to the larger amount of work expended in creating the shear bands and the grace, and to the shielding of the crack tip by the plastic zone. So this is one classic example where how the crack growth is retarded by the plastic zone formation. In a metallic material, we would have attributed this to a plastic zone which is quite big, right? Here we are talking about a craze formation, craze and shear bands. So that is something which is similar to what we are discussing in the metallic materials. So with that, I will stop the brief introduction on semi-crystalline and amorphous materials and highly brittle materials. I have not gone into details, which is not required in this type of a course, but at least some glimpses, some highlights are to be known. So don't worry about the details, but at least try to see whether you are able to see what is happening, at least some highlights, some basic idea when you look at the material spectrum, how we are able to appreciate this. That was my intention. Thank you.